Good afternoon, everybody. Welcome to class. This week we're starting about, or this week we're talking about managing CPUs in virtual machines. So essentially what we're going to be doing is we're going to be extending some of the things that we talked about in our live stream session roughly 3 or 4 weeks ago. When we discussed virtual hardware. If you remember all the way back when I made a mention that at some point in the future we would discuss virtual CPUs in a bit more depth, that day is today. But before we start in on that, I would like to say that today is the first day of registration for returning students. So I want to call all of your attention to that, make you aware of it. You want to make sure to try to go ahead and get in and register for the classes that you need as quickly as possible, just to make sure that you can get what you want. I don't recall seeing any of you at the advising day this morning, which is fine. I know a lot of you being, all of you being online students, you have work and you have other obligations and you have things to do. So the fact that you couldn't make it to advising day is completely understandable. However, it is open registration now. So you want to make sure to try to get in there and get registered. And with the schedules kind of playing out the way they're playing out for spring, it's my suggestion that you want to try to get with your advisor or get with one of the instructors as soon as possible to get a little help working out your schedule for the spring. Things are a little different for this spring. So I want to make sure that you all are able to get what you need. And because I know a lot of you, I think all of you, are trying to graduate this spring. So we want to make sure that happens. So once again today we are talking about virtual CPUs. We have our objectives for today's stream here on the screen. We want to understand how virtual machines use CPU resources, which again is going to be some exposition, some expounding upon what we've talked about previously. We're going to talk about configuring CPU resources in a virtual machine. We're going to look at some CPU tuning practices, and we're going to look at hyperthreading in virtualization. So some fairly deep concepts when it comes to virtualization and all of this fun stuff related to CPUs. So when we're talking about a CPU, we are talking about the central processing unit. It's the computer inside the computer, the thing that turns data into information. And really, when we're thinking about it, along with the memory, the network input-output, the storage input-output, the CPUs are some of the main resources that are used to help size and then determine how well a server or a host machine is going to behave, or how well it's going to work. When you buy a computer, when you go to the store and you buy a computer, one of the key things that you look at in terms of, what am I buying here? One of the key things that you look at is the processor. How many gigahertz of processes can this processor complete? What's the clock? What's the clock speed? How can we? What kind of speed will this computer be based on the processor? it's an important thing, especially for those of you PC gamers out there who have your gaming rigs with the Intel chips in particular. You know how important the difference between an i3, an i5, an i7, and an i9 is. And we also can take this and we can merge it with our concepts of virtualization. Because one of the core properties of virtualization, if you remember Popek and Goldberg, it's that there should be little or no difference in the performance between the virtual machine and its physical counterpart. So if we have a virtual machine and we were to have a similarly resourced, a similarly spec'd out physical machine, they should have little to no difference in performance. But one of the things that we're kind of looking at here is the concept of contention. In a virtual machine, we end up with resources suffering what we call contention when some of the virtualized resources are constrained in their ability to put out their fullest power. Put out the what's the word that I'm looking for? Put out the performance to the fullest extent of the resource. It's constrained. So if we have a virtual machine that's suffering that contention, then the entire performance of that virtual machine will be degraded. Even if it's just one resource that's bottlenecked. Even if it's just the memory or the hard drive or the CPU. So when we consider the CPU in the context of virtualization. Hi, Jorge. Good to see you today. When we consider the CPU in the context of virtualization, the question really is, how do you virtualize a CPU? And the short answer to that is most of the time you actually don't. There are virtualization solutions that attempt to emulate the CPU itself, but emulation in that sort of way often suffers from performance issues and scalability problems because large amounts of processing overhead are devoted to the effort of actually virtualizing the processor itself. So instead what we end up having is the hypervisor scheduling slices of time on the available processor in the physical host for the virtual instructions to run. So what we have here actually looks somewhat like this. One virtual CPU is one physical CPU core. Even though virtual CPUs aren't mapped to physical CPUs. But I think that's kind of getting ahead of myself. Take a step back, because I want to talk about the image there first. Again, that virtualizing a CPU is the hypervisor scheduling slices. So essentially what we're seeing in the image here is a good example of what we're talking about there. The first virtual machine needs to execute a set of commands on the hardware, right? And that request is directed to the hypervisor. So that's kind of what we're seeing. Let's see, did I turn on my screen drawing software? I did. So that's kind of what we're seeing here. This virtual machine, in that regard, is in need of executing a set of commands on the virtual hardware, so it's sending it to the hypervisor. The hypervisor then schedules an execution session for that virtual machine's request. So as it passes through the hypervisor, it's all kind of happening in seconds, right? Or split seconds, really, nanoseconds. But this hypervisor is acting as the go-between between that virtual machine and the physical host CPU. And so essentially, the hypervisor is kind of raising its hand and saying, hey, CPU, I've got some processes here I need to run. If I could have a moment of your time, if you could please execute these processes for me. So the physical CPU then executes those processes, and the instructions on the associated data are passed then back through the hypervisor and returning to the virtual machine. Back that way. In this way, the virtual machines are serviced in a timely and efficient manner, while the physical resource, that CPU, is also being utilized effectively. So it's another instance of our our hypervisor kind of acting as our conductor. When you think about like an orchestra and how the orchestra plays together and different parts of the orchestra are playing different things at the same time, and you have the conductor of that orchestra there coordinating different things. We've talked about this before as our hypervisor kind of plays this role of conductor, where it's coordinating the efforts of the virtual machine and the host resources. In this case, kind of saying, hey, CPU, need a little bit of your time. Got some got some processes I need to run. Can you run these real quick for me and give me the data back? And the CPU is just like, hey, I gotcha. And then on to the second point there, which I got a little ahead of myself on a few minutes ago. A virtual CPU is equal to one physical core of your host CPU. But in other virtualized stuff, they might be mapped to certain things. We talked about hard disks kind of being mapped a little bit to the physical memory. In this case, it's not really mapped to any particular physical CPU, since we're not having a particular CPU that's running something for the virtual machine. We're just scheduling time. But one physical core is one core of our virtual CPU as well. So if each virtual machine then had only one virtual CPU and each physical machine had only one physical processor, the model would be simple. But in reality, everything is multiplied. It's much more complex. Modern CPUs come in packages that are multiple processors. And this doesn't really greatly affect the model that we kind of previously looked at, aside from providing additional resources in the form of CPU time that can be allocated by that hypervisor. So in our chart here, we have an explanation of cores available in various processor configurations. And essentially what you need to know here when we're dealing with multi-core CPUs is basically just that adding more cores to each CPU adds more available processing resources for the virtual machines to utilize. Remember again that nothing's mapped directly to any certain core or any certain processor. It's just taking processor time. I mean, we can do some rough mapping when planning for resources. Because, we can say, because when we have all of these different resources, we can kind of look at what our machine needs and we can adjust our machine accordingly. But it's not going to be direct in terms of mapping like one might think. So let's talk a little bit about configuring virtual CPUs. And we're really limited in what we can do in terms of what we can configure with a virtual CPU. There are very few items that you can adjust here to affect the virtual machine's performance. Really, there's only one, and that's the actual number of CPUs. Now, one of the great things about virtualization is that with certain operating systems, we can actually hot add additional CPUs. So if you put an operating system on a virtual host, a particular one, it doesn't necessarily work with all of them. The example given here is a Linux server. But Windows, I think Windows Server will also work. You put the operating system on there, you decide, these aren't really good enough. This isn't really good enough. It's not really processing the data fast enough. I need to, get this time allocation a little better. And so you can actually hot adjust the amount of virtual CPUs that you have on a virtual machine, and that's what our image here is showing. And this was actually a relatively recent addition to virtualization. The fact that you could hot add CPUs to a virtual machine. Not too recent in the grand scheme of things. I mean, we're looking at, 2007, 2008, and later. And this really came as an innovation in operating systems more so than an innovation in virtual machines themselves. The operating systems actually began to support hot adding virtual CPUs. So prior to this, you would actually have to cold add any new CPUs. So you'd have to power down the machine and add the CPUs at that point. Now currently, to my knowledge, you can't go the other way. You can't reduce the number of CPU resources in a running virtual machine, which makes sense when you think about it. Because it's, processing things at a certain speed. You can kind of speed things up by giving it more room to run. But slowing it down would, in turn, cause a crash more likely than anything. So if you wanted to reduce the number of CPUs running in your virtual machine, then you would need to shut down your VM, change the numbers, reduce the number of CPUs in your machine, and then restart. And it makes some good sense when you think about it that that's the case for reduction. But again, and to our final point here, different platforms support different numbers of CPUs in a VM. It's going to be based on the operating system and the operating system's ability to recognize CPUs and that sort of thing. So your operating system in that regard is going to be the limiting factor as to how many virtual CPUs are supported in a particular virtual machine. So here we have just a few pieces of information for you. When sizing a virtualization host, since a single physical CPU is not 100% busy, one physical CPU can service multiple virtual CPUs. And so, that's to kind of be expected with everything that we've talked about with virtual CPUs versus physical CPUs so far. We can kind of utilize cores as their own virtual CPU, have the different cores process, have time on the different cores, process things from different virtualized hosts. So if the physical CPU is not 100% busy, which it should not be, then one physical CPU can service multiple virtual CPUs. Now, in that sort of way, however, you have to be considerate of the amount of workload that you're putting your physical CPU under. And you have to kind of be aware of the limitations that, this kind of, that the CPU has. Because you have to, with several different virtualized hosts running, all executing processes at the same time, you can easily kind of overwhelm a physical CPU. And in the event that that happens, you kind of understand the rest with your history of knowledge of hardware. You overwhelm the CPU, bad things can happen. But if we have a 4-processor quad-core system, so that's 4 processors, each with 4 cores, we can run 16 virtual CPUs, which, the math checks out, right? Because each one of those cores we can use as a vCPU. So we have 4 processors, each with 4 cores. 4 times 4 is 16. The math works out. That's working at a 1-to-1 vCPU ratio. However, we can configure multiple virtual machines to utilize the same cores. So we can utilize 5 virtual machines on 1 core, or 10 virtual machines on 1 core. And in this instance, you want to be aware of the workload that you're putting these cores under. But if they're able to handle the instructions as the hypervisor kind of schedules it and works everything back and forth, which is why we're able to do this. Because remember that we're not solely dedicating one CPU to 1 core. We're taking slices of time. So we can have 5 CPUs for 1 core. We can have 10 CPUs for 1 core, as long as they're kind of coordinating their time usage and all that sort of stuff. So we can run 80 virtual CPUs in a 4-processor quad-core system at a 5-to-1 ratio, or even 160 virtual CPUs on a 4-processor quad-core system. So, that's pretty incredible there when you think about it. A 4-processor quad-core server is essentially what we're thinking about there. If we ran that 10-to-1, we could run 160 virtual machines off of that system. Which is fairly incredible. But that's if you just do single processor virtual machines. What if you want multi-processor virtual machines? So a virtual machine with multiple virtual CPUs needs to schedule time on multiple physical CPUs. Additional virtual CPUs might hinder performance depending on several different factors, including physical resources and CPU contention. So you get those CPU constraints causing a bottleneck. That's that contention again that we talked about at the start of this class. When you get that contention, it hinders performance. So the best practice then is to configure one virtual CPU to a new virtual machine and then increase the number if you need to, rather than start higher and go backwards. Which also makes a lot of sense, considering what we talked about in relation to how we can hot add vCPUs to certain operating systems, but we can't hot decrease. So if you start low and go high, it's a more efficient way to employ multiprocessor virtual machines than the other way. That way you're making sure that each machine has what it needs before trying to allocate something else. In creating multiprocessor, multi-core virtual machines, what we're talking about is equivalent in performance to multiple single-core virtual CPUs in capability. But this is sometimes done for licensing reasons. You know, sometimes you have software licenses that require it to be on a multiprocessor, multi-core machine. And we can virtualize that. But when we virtualize it, it's going to have the same impact. It's going to be inequivalent performance with a multiple single-core virtual CPU, more or less because that's just the way that it works out. And so we're going to talk a little bit about hyperthreading. And I think we're about to the end of our time here, so just kind of bear with me. So hyperthreading is an Intel technology that provides better CPU utilization. So prior to hyperthreading technology, essentially only one set of instructions could be executed on a processor at one time. For each physical processor, hyperthreading presents two logical processors. So in a way, hyperthreading kind of virtualizes the processor, but not on a virtual machine. Because, you know, we said back at the beginning of the course, essentially what we're doing is we're making physical things into logical things, and that's virtualization. So with hyperthreading, we're taking a physical processor and we're turning it into two logical processors, and each of these logical processors can process an individual thread of work. So for each physical core, two threads of work can be scheduled. Now this doesn't double the capability of a processor, but under the right circumstances, we might be talking about like an extra, say, 30% efficiency. Even though it kind of appears to double it. And we can use hyperthreading with virtual machines. There are some prerequisites, however. One is that the operating system must support multiple processors. Windows and Linux do this, as do most hypervisors. And then the operating system must support hyperthreading. Again, Windows and Linux and most hypervisors support hyperthreading. So the operating system has to be able to support multiple processors, and the operating system has to be able to support hyperthreading as well. Most modern operating systems do both of those things, and most modern hypervisors do all of those things as well. There are instructions out there that you can utilize online if you want to check to see if hyperthreading is enabled on your device. A simple Google search can get you to what you need to see if you have hyperthreading enabled. Just to give you a little bit of information on that. So it might be something that helps you out with a little bit of performance as you make some more process-intensive virtual machines. And we'll wrap it up with this right here in talking about Intel and AMD processors. Both Intel and AMD chipsets work well for virtualization. I think by now most of you have probably realized that as we've been creating virtual machines on our desktops. Whether you have an Intel-based CPU or an AMD-based CPU, they both work. We can actually move virtual machines from an Intel server to an AMD server if we want, but we can't. Well, we have to do it cold. We can't do it hot. We have to shut down the virtual machine in order to transfer it. And that's only because the command set of the different chips are different. If the chipset is the same, so Intel to Intel or AMD to AMD, we can actually live migrate a virtual machine from one server to another. So when you're looking at a big server farm that consists of a bunch of virtualized devices, so like if you considered like here at Cleveland Community College, where we have our servers that run our devices for our Zero clients. You know, all of the servers that have all of these virtual machines on them are typically one type of chipset because of the fact that you can live migrate from one server to another server. You know, this also helps you with things like redundancy. You know, being able to have backups. Being able to move from one to another quickly and easily to make sure that there's no downtime. And as you all have discussed in other classes, the criticality, the importance of having little to no downtime. We're able to do that with live migration for virtual machines on servers with the same chipset. So in wrapping up this stream, these are the things that we talked about today. Virtual machines use scheduled time on physical processors of their hosts. Virtual machines can have one or more CPUs. Multiple virtual CPUs are not always preferable. Poor configurations can magnify performance issues. And virtual machines can, in fact, use hyperthreading. So that's where we're going to leave it off for today. Once again, I'm going to remind you all to try to register as soon as possible. So as to make sure that you get all of the classes that you need. I'm going to turn the music back on and stay in the chat for a minute, answer any questions that you have, if anybody has any questions. But I want to thank you all for coming today. And that's all that I have. I will see you next time. I'm crazy, I ain't just a psycho.
tell her how far I'll go, so they better lie low. Mind racing, I'm crazy, I ain't just a psycho. Yeah, 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 psycho. Time, lingering, pondering, save your space and wine. You are not a tree, just move if you don't like where you are, where you are, where you are. Every time I think about all the things I live without, motivates me. It's a do or die. Fuck fear, no fear, it's worth a try.
I lost people over petty shit, I don't regret it. And every time I think about it, all the time my heart forgives. I have given everything, but it's not enough. Fuck fear, no fear, my heart can't stop. 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 Erase your every morning. Just open up your eyes and you'll see that there's a meaning to the love-hate relationship. To the haters that was that great.